All right. Hi, everyone. Welcome. We host a lot of meetups actually here, but I'm particularly interested in this one. I wanted to just kick off with just a couple of minutes on who MuleSoft is. So my name is Uri. I'm the CTO here at MuleSoft. We're a large-ish startup, if you like, about 650 people or so right now, 300-something people a year ago. So we're still kind of young, but growing pretty fast. We're an enterprise software company. We're in the business of putting APIs on everything and helping you connect them together. You can call it integration, you can call it connectivity, you can call it APIs. And what people end up forming with us is something we call application networks. So networks not at the IP level, but at the application level, at the business level, creating these reusable building blocks that allow large companies, small companies to kind of reassemble, recompose themselves. And we serve mostly larger companies, but we've got smaller ones as well. Tesla, Wells Fargo Bank, a number of these companies. And the reason why I'm particularly interested in actually the two talks that we're hearing today is it's an interesting combination of big data and containers, if you like, or Kubernetes, or kind of Docker or microservice, however you want to call that space. And as being a provider of a platform for application networks, one of the interesting things that I really find is the amount of data that ends up flowing through our platform is remarkable. We ship, for example, 60% of the prescriptions in the US goes through our platform. And this is on-prem and on cloud, but what's really interesting is that when you have something that's the fabric that connects all your services, inevitably data flows through your stuff. And I don't think we've even begun to scratch the surface of all the value and interesting things you can do when you have that kind of visibility on sort of the whole wiring background of large companies. One of our customers, HSBC, has 30,000 people in their IT department. I can't even imagine what a 30,000 person IT department is. I can tell you there's a lot of stuff there. And it must be interesting to go ahead and take a look at that. And the other thing is really, we're leaning very heavily into containers, into Docker, into Kubernetes, into a variety of kind of orchestration things at scale. And we're actually thrilled to have Gravitational here. It's working with us, the second talk of this. So the stuff that we're doing, I think, is pretty interesting. It's somewhat cutting edge. It's not cutting edge in the sense that we have to invent new algorithms. But what's nice is that the market is mature enough where we can actually rely on technology like Kubernetes to build things at scale and do some really interesting things with them. Hopefully some of that we will hear about today. So I'll shut up for a little while. Obviously we're hiring. So if you're interested in any of the stuff that we're doing or engaging in some interesting technical conversations or how are we thinking about this or that, there's a few people here from MuleSoft. Maybe people can raise their hands. Just find any of the people here and engage us in conversation. Thanks a lot for coming. What are we doing with microphones? You got your own?
No, I need this one.
There you go.
Thank you. All right, and we have made it through no audio video errors. Okay, wow, we've got a lot of people here. So first off, thank you MuleSoft, thank you Alpine for organizing this and for having us. This meetup is all about streaming pipelines. And so with Pachyderm, what we're going to be talking about are particularly big data pipelines where we analyze data. And as was just mentioned, this talk is very, very heavily focused on containers. So this is the name of the talk. And as was just mentioned, I'm Joe Doliner. I'm the founder and CEO of Pachyderm. Before that, I was at Rethink2B. I was actually their first engineer, and I was at Airbnb, helping them out with running the new that. So, first off, this slide is about what's Pachyderm, but actually before that, I just want to sort of take the temperature of the audience and ask, so who here has worked with containers, with container technology? technologies. Okay, awesome. A lot of people. Would anybody like to sort of throw out a definition of what a container is and what it does for those that haven't worked it with it? Right there. Throw out a definition for what a container is.
Container is a separate part of application which separate this application outside of any I got this. Sorry.
You're not confused actually. You're basically right. It's about separation. You want to take another crack at it?
A real simple way would just be say less than a virtual machine more than a process.
That's a great way of saying it, actually. So both of those technologies, right, virtual machines, processes, they're about separating like one piece of code from another, and that can be for security reasons, for dependency reasons, for multi-tenancy reasons. Containers are a new and very popular way to do this. They're mostly new and popular because of Docker, which is a company that has really sort of pioneered all of the use cases surrounding containers and made them much more useful to people. We're going to be talking heavily about containers and actually using some of them in this talk. So just wanted to make sure everyone has a definition of what that is. Okay, so what is Pachyderm? Well, Pachyderm is basically big data with containers. And what we mean by that is that containers are sort of the core unit that you use to use Pachyderm. We wanted to make a system where all you had to do to run some distributed analytics code was to put that code inside of a container. And this was motivated by sort of these endless struggles that I had at Airbnb, where I'd have these two users who had written different analytics code that required different dependencies, and installing those two jobs on the same Hadoop cluster was an absolute nightmare because you can't really comfortably install all of their different dependencies. So that was sort of the initial idea that got us thinking about like building a new data platform and building Pachyderm. Along the way, we realized there were sort of some other features that we needed to make all of this work and make it work together. The first one we realized was we wanted to build version control for data. And that's actually a very interesting feature that sort of interplays very well with streaming pipelines and with the containers that we use to build them. Everybody's familiar with Git, okay? We don't need to go into that one. Yes. So Git is basically version control for your code. We all use it. We all use it to push to GitHub. There isn't really a common system like that for big data sets until now. Basically, what we wanted to build with Pachyderm was something that can do that up to sort of the petabyte scale, right? And so that we could have these large data sets and they could be controlled in these ways that Git was. I already mentioned that we wanted to use the containers for data processing, but once we realized that we were sort of using these containers and that we had version control in our system, we realized we had the option to do something really cool with our system, which is that we could blur the line between a batched and a streaming job. Right? Remember, in a batch job, what you're doing is you've got some huge data, some data sitting there, you want to just process it, tear through it, and then you've got data sitting somewhere else that you output it. In a streaming job, you've sort of got this ever-changing data set, right? And as new data comes in, you want to process it and put it somewhere. Version control allows you to blur the lines between those two because it allows you to sort of see, I've got this big data set, but here's how it changed. Here's what's new. Here's what's changed since the last time I ran this computation. And so we're going to be doing a live demo where we see exactly that type of a thing in action. And then the last few details like that is with Pachyderm, all of the data lives in an object store. So like S3 or GCS, we don't like handle the redundancy ourselves. And this sort of makes it very, very good for deploying on cloud infrastructure like AWS and GCS. And lastly, because people often get confused, and this is part of the talk, Pachyderm is meant to fill more or less the same need as Hadoop. It shares no actual code with Hadoop. It's a completely new system. It's not written in Java, it's written in Go. It uses sort of etcd instead of Zookeeper, those things. Any questions on this one? Oh, all right. So actually, we've already sort of had an intro to containers. One thing that I don't think we've had an intro to, although we did talk about it a little bit, is Kubernetes. Does anybody want to throw out a definition of what Kubernetes is? Kubernetes sometimes. Sure, there we go. Fellow speaker.
It's an orchestration system.
Exactly. So it's an orchestration system, and as you can sort of guess, the thing that orchestrates is containers. If anybody has worked at Google or sort of is familiar with their internal projects, it is the sort of religious successor to Borg, I would say. And so basically what Kubernetes does is it gives you these incredibly high-level primitives for which to do distributed systems with containers. You can tell that I want 10 copies of this container running somewhere. I don't care where, just like find some virtual machines that I've given you and put them on it, and Kubernetes will handle the rest. It also will let you run a job. That's very, very useful for us in Pachyderm because we run jobs too. And actually, a Pachyderm job is really just a Kubernetes job with a few extra things added to it. So what does version control for data actually let you do? There's a couple of very, very key features that this allows for data science that were appealing to us and were the reason we wanted to build it. We've already mentioned the one that allows you to blur the line between streaming and batch processing. The other thing is that it just lets you view diffs of data, right? And this can be really, really useful if you've got like petabytes of data and you want to see like, oh, is this data that's 95% the same as yesterday, or is this data that's 2% the same as yesterday? It's very, very useful for collaboration. And this sort of makes intuitive sense because that's what GitHub is, right? GitHub is a site for collaborating on data science. That problem gets a little bit more tricky. Or sorry, GitHub is a site for collaborating on code. We're a system for collaborating on data science. That's the big difference. But we ran into this problem all the time at Airbnb where we would have sort of a data set that was just sitting in HDFS, and then someone would want to come in and do some analysis on it. And they'd have this really big worry that this data was about to change from underneath their feet because data was constantly changing. And so what they do is they make a copy of that data, which is a natural thing to do because now your analysis is stable. But the issue with this is that then a month later when they go to compare their analysis to another person's analysis, you can find that like you disagree vastly on the number of users that this company has or the amount of money that you made last month. And that gets really difficult to track down. And so I saw that system was like, well, what we really want to be doing here is forking and merging, right? We want the system to sort of manage our process of freezing this data, knowing how it's changing and stuff. And so that's a big feature that we enable. And then the last one is provenance. And so who wants to throw out a word for the definition for the word provenance?
It's where it came from, the genealogy, history, or something like that.
Exactly. Yeah, so and if any of you have taken French, it's actually from the verb provenir, which just means generally to come from. So yeah, provenance is the notion of where things come from. And when we're talking about data, we're talking about if I've got a data set over here and I compute something with it and create a data set over here, well then this data set is the provenance for this data set, right? And that's useful to know because you can sort of answer questions in both directions, right? One, if I've got two pieces of analysis that disagree about like something basic like users, I can say, okay, well let's see their provenance. Like, did they come from the same data? If not, well, that's the problem. And then if they did come from the same data, that's like, okay, there's probably some problem in this analysis here. And it's useful in the other direction when I just say, I've got some data over here, I want to see all of the things that everyone in my company has computed from this so that I don't compute the same things. And so Pachyderm actually keeps track with all computations. It keeps track of the provenance that's accrued between them, and it lets you basically traverse that graph in both directions. Any questions on right there?
But so just so I understand, so when you view diffs of data, that's for like data at rest. Like you need to continuous monitoring of the different, difference.
Yeah, so you can view a diff of data at rest. You can also subscribe to new diffs as they come in, and the system will basically alert you, hey, there's a new diff here, here's how you find it. And that's a system that our jobs use internally, basically to keep pipelines up to date. And we'll see that in action in the demo, but basically, yes, you can both think about diffs of things at rest and then diffs of things to come in the future. Right, that's a great question. Anyone else? Yes?
You handle destruction of data?
Destruction of data. We do in some limited ways. By destruction, you mean sort of like deleting and removing it
Forever.
forever, just
From the history.
from the history, like scrubbing it clean. Not in a rigorous way yet. Not in a good enough way where it's like you could need sort of legal compliance with the user. Like you must forget this user completely. We don't do that yet. Great question. Anyone else? All right. So sort of piece one of this is this version control data. Piece two is actually building the pipelines out of it. And when you're talking about pipelines, there's sort of a couple of things that you want to be able to do with the system. One of it is basically just making a DAG, right? And by DAG here, I mean directed acyclic graph. So basically, like data starts up here, and it might branch out into a million different jobs, and then those each create some other data, and then some other job depends on a bunch of them. So you can see here that sort of, it goes from task 1 into tasks 2 and 3, and then task 4 sort of splits into task 6 and a dashboard, just consuming them. You need a system that understands all of these dependencies and knows how to execute the pipeline with them. Pachyderm does this, and it does it basically using, again, the version control semantics underneath. So in Pachyderm, each one of these tasks would basically get their own repo. And that's sort of an atomic set of commits that exist. And what's really cool about this is that we have this entire pipeline that we want to run to completion, but we don't need to run it all to completion in one go, right? So if we have a few tasks that complete and then the entire system crashes, that's all fine because we've snapshotted all of these intermediate states inside the system because it's all version control. And so when you bring the system back up, it'll just pick up where it left off and can complete those tasks. This leads to processing efficiency, right? Because you don't need to compute things. And then there's also this processing efficiency that comes from the fact that you're computing things just on diffs, right? So the system is smart enough, as I mentioned, to figure out, oh, I want to compute something over this data set, but I already computed that same thing over 99% of this data set. So I really just need to compute on this 1% of new data that came in, and I can do that much more efficiently. The word we use for that is incrementality, which will be coming up a lot. Any questions on the data pipelines? Okay, we are at the demo. So I'm going to move this over to my terminal.
Quick question.
Yes.
I can clearly see the use case for analytics. Is the use case as compelling for machine learning and predictive modeling, or?
Yeah, we think it's really compelling for machine learning. To be honest, we're not the most experienced machine learning people, so we're kind of basing this on discussions we've had with people who know more than us. But the main things that have been compelling to them is one, that you can retrain very quickly because you can sort of like use incremental things. But then also just sort of being able to like automate the whole process of like new data comes in and like having that version control, like version controlling your model so you know which model came from where.
I'd be happy to talk more about that.
Awesome, awesome, I would love to. Okay, so now we have the one issue that I need to type.
We'll give you a timestamp.
Okay, she's gonna give me something to fix this problem. I'm gonna.
In the meantime, yell.
Yeah, is this too quiet for anyone if I use my big person voice, or does that work? Okay, so we have here actually a running Kubernetes cluster. And I can show you that right now with kubectl get all. And then it's a little bit too big, so it's wrapping, but you can see here that I have two Pachyderm nodes that are running right there. And so the command that I'm going to be using to interact with Pachyderm is called packcontrol. And you can see here, okay, let's just take, cool. Okay, we're good. So as you can see here, I just did a command packcontrol list repo, and it returned to me an empty output. And that's because I haven't created any repos yet. First, I should tell you what a repo is. It's basically the same thing as in Git. It's sort of a bunch of data that all goes together according to some schema that we all have in our minds. In this case, what we're going to be doing is we're going to be doing sort of what we call the fruit stand demo, which is we have this faux fruit stand that is selling fruit to people. And every time it does, they have a little system that logs a line showing them how many of the fruit they sold and which fruit it was. And so we're going to put that data into a repo, and then we're going to make a pipeline that processes that data as new fruit is coming in and counts up how many of each piece of fruit is sold. So the first thing I need to do is I just need to create this repo. And I'm just going to call it data. And so now when I do list repo, I can see that I have something there. And the next thing is, in order to write to this repo, I need to start a commit. Now, this is a place, you may notice, where we're a little bit different from Git, because in Git, there's no notion of starting your commit, right? You just commit. The reason for this difference is that in Git, you basically have your local working directory, right? And you modify changes to that, and it just knows that those changes apply to what you're doing. In our system, a diff could be several terabytes big, so you can't just save it on a local system, and it's sort of enough storage that you need to like explicitly ask for it and explicitly close it, because you can't just leave that around safely. So I've created this, this commit, and now what I'm going to do is I'm going to, first let me show you what these data files look like. So this is an example of the data file. And as you can see, it's got 3 different types of fruit, banana, oranges, and apples, and each line is just the name of the fruit and then a number that indicates how many of that fruit I sold. And so what I'm going to do is I'm going to take that and I'm going to put it inside of that repo. I'm going to put it in a file called sales. And now I'm going to finish the commit. And so now if I go back and look at the repo, I can see that there's actually some data in it. And I can actually now mount this data for you on my local file system. And so by doing that, what I've done is the directory PFS in my home directory is now a mirror of the data that's in there, right? And so if I look in data, I'll see a folder for the commit, and then I'll see my file in sales. And if I cat that file, I should get the same thing that I had before. Cool? Any questions about that?
For your typing question.
Yes. And we have a question. Yes, back there.
So, what is the advantage of this system over all the checkpointing and recovery systems that have been designed for, you know, large, high competing systems like weather forecasting and all that? I know you're using newer technology like Kubernetes and all that. I'm just trying to figure out how this, you know, what the advantage of this new technology is over the established checkpointing.
Right, so the checkpointing, I'm not familiar with that well actually with all the checkpointing and recovery systems in high performance computing, so I can't speak specifically about that. One thing that I imagine is a pretty big difference between them is sort of the like orchestration of containers as the main job flow, and the fact that it can sort of show the containers a diff of the data, and then, well, and also just the fact that you can put all of your code in a container so you can use it with any tools. I also don't know like if they do sort of diff-based computation or not. But yeah, that's sorry, right there.
How long will it take of adding the file of 300 gigabytes?
How long will it take for adding a file of 300 gigabytes? We've seen people get a sustained throughput of about 300 megabytes right now per second. So that works out nicely to be about 100 seconds. I believe, did I do the math wrong there? That's 1,000 seconds. Yeah. But yeah, so we don't unfortunately we're unfortunately not at the stage where we have like rigorous benchmarks that we can show you that have sort of tested that at large scales. So I can't say precisely. Anyone else? Okay, so we've got a repo and we've got data in it. And so now the next thing that we need to do is we need to actually process this data. We need to do something with it. And to do that, we're going to create a pipeline. Pipelines in Pachyderm are defined using a simple JSON format. And so I'm going to open up the pipeline that I'm going to create. I guess I have this open somewhere else. So this is a pipeline. And as you can see, as I said, this is a simple JSON format. And I'm going to walk you just through each step of this pipeline so we sort of know what's going to happen. First off, you can see right here, we're naming the pipeline filter. And the job of this pipeline is to take sort of all of our data in sales that is homogeneous, that includes information about apples, bananas, and oranges, and separate them out into just apples, just bananas, and just oranges. And you can see down here that the tool we're going to use to do that is grep, because there's no real need to use a nice fancy tool when we can just use a simple command line tool. And now I'll draw your attention to one key feature of this, which is that if you notice, this call at grep is reading from /pfs/data/sales. Now, what that is it's a fuse mount that our system puts into the user's container while the user's code is running. So that same system that I just used to mount it on my local system on my Mac, we run that inside of the container. And so your data in the cluster is just displayed as a local file system. And so it's reading from data, because that's the name of the repo. And then it's writing to out. And out is actually going to be a repo called filter to correspond with the pipeline. But inside of the pipeline, we just refer to it as out, and it sort of maps it all to the right place. And so the point here is that it's sort of computation as simple as just reading and writing to disk. And our system can be very smart about when you scale up this container so that it runs with this job so that it runs in more than one container. So if you had 4 parallel containers, then this file sales in there would, for each of those containers, only contain a subset of the data. And so they would be processing it in parallel, and then at the end, all the data that goes into apple, banana, and orange, that would get concatenated together at the end. Lastly, so I'm specifying the parallelism explicitly here, that I'll just have one container running. And then lastly, I've got this input section. And what this is just specifying is that I want the repo, the data repo that I just created, to be visible to me, and that I want to do this with a map method. And this is sort of harkening back to the map-reduce dichotomy that you see in Hadoop, that you see in functional languages. It's still that same concept. When you're filtering things out, there's no need for things to be on the same container, right? It's just, you can do that completely distributed. All right, so that's the first step in the pipeline. Any questions about that?
How do you map the actual commit in your local folder to these? Is that part of the container?
So that's part of our system, basically. So the way that we do it is when I mounted, so when I did that mount on my Mac, that was using Fuse to mount that. We used that same code inside of the containers. And so what we're doing is we're taking a user container, we're taking a command to run in it, and we just, before that container starts running, we put in that local Fuse mount. We set up the mount inside the operating system, and so then the data is visible.
Yeah, but your local mount shows also the commit as part of the path, right?
Right, so the local mount lists the commits. So we can sort of mount in 2 ways. We can mount the whole file system, in which you see all of the different commits, and then we can mount a specific commit for the repo, in which case we just align that commit name. Yeah, that's actually a very sort of subtle detail, because if you don't have that, then there's no way for you to write a valid job, because you don't know what the commit's going to be ahead of time. So yeah, we need to align that. That's a great catch. Right there.
Is this file system-centric example just to keep things simple, or does it generally work best with processing that starts and ends at the file system? For example, like Elasticsearch, which puts everything into a bunch of tiny files or databases.
So this isn't really to keep things simple. This is sort of the cool the core interface that we exposed to Pagner. Which, I mean, we exposed this interface because we thought it was simple. So in that regard, it is toward that end. But so just sort of to be really clear here, this is not actually like a real file system that stores the data inside of the container. As soon as it writes to a file in there, that becomes an RPC that goes into like the distributed file system. And so using that interface was the core interface we sort of envisioned for the system. And the reason for that was basically that we wanted to make a system where it was sort of equally accessible to all different languages. And the one interface we could think of that works in every single language is, well, every language knows how to open a file from the file system and speak that language. And so this was sort of a very good, like, democratizing interface to things. We're planning to add some of the sort of more traditional things, like a real MapReduce implementation with like a map method that takes key value pairs and stuff on top of this, which should be pretty easy. Right there.
Do you consider data locality?
Do we consider data locality? So that is a great question, and the answer is that we do not. The reason being that this data is actually all stored in S3. So we wouldn't sort of know what data locality meant even if we wanted to, because it's not like S3 is local to one node. This was actually one of the big discoveries that we made throughout the course of the last few years. Was in our first implementation, we actually did respect data locality quite a bit and felt that that was a really important feature because that's like always held up as one of the hallmark features of Hadoop. And it wasn't until I talked actually to my roommate who works at Google, and he told me that Google had sort of abandoned the concept of data locality in their MapReduce implementation a few years ago because they found that inside of a modern data center that was basically never the bottleneck. And so we basically took that as a cue that we should rethink exactly that same assumption, and so we did.
So it looks like there's data stream coming in and stream coming out. Any other notion of a structure for the data? And I wanted to read from archive files. How would you handle it?
So basically, we just think of the files as a stream of bytes, and then you can sort of put data, you can put data structure on top of that, right? So a Parquet file should work fine because it's sort of like Parquet knows how to take a stream of bytes and turn it into Parquet, and you just put that inside of the container. That does get interesting for us with, so digging into the internals of this a little bit. The one sort of question that's hard for us to figure out is if we've got a file, like imagine this sales file with several terabytes, right? And we want to spread it across 10 different containers. Well, the question that we need to figure out is how can we chunk this, right? And if it's a Parquet file, then the thing that you don't want to do is like chop one record in half in the middle because then you 2 containers get half of it and neither one can actually reconstruct it. And so that's actually a feature that we're adding in 1.1 is a way to have sort of different custom delimiters that are specified for that chunking operation. Right now it's all just line-based, which works great for the fruit stand demo, but wouldn't work for Parquet. It's a great question.
Is that the image field?
Yeah, so I sort of glossed over this right here. You can see there's an image right here. This is just this is the Docker image that actually gets instantiated and runs in your container. Fruit stand is one that I've made locally. It's actually basically just an Ubuntu image because I'm just using like grep and stuff and I don't need anything special. But it could in theory have anything in it. All right, let's do the second half of the pipeline and then run this. So the second half of the pipeline is a little bit more complicated. First off, you can see that this part is called sum, and as I mentioned here, the goal was to sum all of these things up, so this is the thing that actually does it. So you can see here we've got a like 10-line shell script, and I won't sort of give you guys a shell lesson too quickly, but basically all that this is doing is it's calculating the sum of the data in this value new sum. That's the sum of the data that it's processing in this run of the pipeline. And then the old value of it is available in a special commit called prev for previous. And so this is how you can make an incremental reduce pipeline. And so the difference between this and the other pipeline, if you go down here, is you can see that it's taking the filter repo, the one just created, as its input, but it's doing incremental reduce on that. And so in the map world, everything can sort of be done incrementally, things are nice. In the reduce world, things get a lot more complicated. It so happens that what we're doing here is addition, and addition is an associative operation, and so you can actually do a reduce that is an addition incrementally. That isn't true in general for reduces, but in this case it is. All right, enough talking, let's actually run this thing. Line. Okay, so I just did 2 things here. First, I created the pipeline, and I just passed that file to it. And then I did pack control list job, right? And so as you can see here, I've now got 2 jobs that came out of here. They both succeeded, so fortunately demo demons didn't strike. And you can see here that they've each got a different output. One of them is outputted to a repo called filter, and one of them is outputted to a repo called sum. And you can guess which stage of the pipeline outputted to which repo. And so now I'm going to remount this. And so now when I look in PFS, you'll see that I've got data with the sales. I've got filter with its commit and the values for apple, banana, and orange. And then I've got sum that also has values for apple, banana, and orange. And so now if I go in here to sum, or sorry, I can see that I sold 133 apples in my first run. So I actually don't know if that's good for a fruit stand, but it seems pretty good. All right, so any questions on what we just did there? Oh, and one other thing that I will show you is Docker PS. So if you see here, there are now, and it gets a little bit garbled, but there are now 2 different jobs that ran, and both of them use the fruit stand image. There's this one and the one up there, right? And those are the containers that Docker instantiated for me, or well, the Kubernetes instantiated. They both instantiated them for me. Those are the things. So, any questions on that, or should we get to the last step where we're going to stream a bunch of data through this and see it all happen live?
Is the pack control, the backend control, the one that talks to the queue control? So when you create the stack with that JSON file, you actually pass that to Kubernetes to create the containers?
So the question there was, does pack control talk directly to queue control? It actually does not. So pack control talks to Pachyderm, and then from within Pachyderm, remember Pachyderm is itself scheduled by Kubernetes, so you can get a Kubernetes API endpoint from within Kubernetes and sort of send commands from within out to the. Sorry, did I change something? Test. Good now? Okay. Yeah, so Kubernetes sort of, we send these commands to Kubernetes from within. We get those endpoints within our containers. Great question. Anyone else? There.
So how do you actually, so you showed the JSON commit ID for the data. How do you actually know that the sum commit ID is anytime connected to which commit ID of the data? Is there any, can you?
Yes, so the question is, how do we know if the sum commit ID is connected to any commit of the data? So I have, let me see if I have it in this version. I think I should. Yeah, so, interesting. So remember the command I was talking about, provenance, before? So basically the answer to your question in general is provenance. And so provenance can take a couple of forms in here. I could search through the sum repo for a commit that had as provenance a particular commit in data. I can also use a command called flush commit. And what flush commit does is it takes a commit, such as the one in data, and it returns all of the commits which have this commit as provenance. And so when I do this, this is a little bit uninteresting right now because those are the only commits in the repo. But in a moment, when I add in a bunch more commits, then you'll see that I'll still be able to flush any one of those commits, and it will tell me sort of the full snapshot of my system that corresponds to that input data. All right, so let's do the last step here, which is this. So I have a little program here called generate that is basically going to do automatically the thing that I did at the start to kick everything off. It's going to create new commits, it's going to put data in them. And so I'm going to tell it to generate 25 commits for me. And while that's happening, I'm going to come over here. I'm going to do the control list job. And why don't we just sort of watch that? And so you can see that I've got this long list of commits that are all running. And gradually, they're going to all go green. Well, except that watch strips out color, so they're all going to change to the word success instead of running. And so when this is done, what will have happened is I just created 25 commits. So Kubernetes will have fired off 50 containers for me, 2 for each step in the pipeline. And it will, it's done now, have basically kept up to date that full sum of the system. And so now, if I go back here and I do bit on data, I'll get a huge line of commits. And let's see which commit corresponds to the most recent one. So if I now flush this commit, you'll see that these are the commits most recent, and now if I do, I can see that after that I sold 4,041 apples, and that's definitely good. Like I don't care what kind of free stand you're running, that's got to be good. And so that's basically the system in a nutshell, and I've now got this completely resilient pipeline. As new data is added, it'll all get computed, and I can even actually, so here we just did sort of a linear chain of commits, right? I can even sort of branch off one of those commits and do one on the side, and that will become a separate branch in all of my cascading repos. And so I can sort of commit something in the middle. And this is that use case that sort of originally started us on this quest is some user is going to want to come into this repo. They're going to want to run analytics on the fruit stand as it was today, even though new data is coming in. So they need to branch off of that one commit and basically freeze it. And then they can just go to town. And at the end, they can merge it all back in, and then that's what the job will run on. And the pipeline will just keep all of that up to date for you. And it'll do so doing the minimal amount of computation, because each time it comes in, it's only doing computation on the diff. And that's it. We got plenty of, or well, how much time do we have for questions? I don't know if I'm cutting into someone else's time here. Let's just start with questions.
You create the pipeline, right? And job started immediately.
Yep.
Is it possible to schedule the job to start at some point of time?
So the question is it possible to schedule the jobs to start at one point in time? Not yet, but that is coming very, very soon. There is one particular use case that I've heard a lot that I know is appealing to people of that type, which is the ability to use spot instances. Basically the ability to like schedule a computation but not do it until tonight when spot instances are really cheap. And so yeah, we definitely want to do that, and we definitely want to be able to sort of use Kubernetes smartness to schedule our jobs. So be able to say like run this job but only put it on this set of machines that happens to have, that happens to be spot instances or something like that.
Yeah, it should be easy.
Yeah, I mean, so the hard thing about delaying execution of a job is basically the raciness and making sure that like the data doesn't change. In our system, because the data is all immutable before you run a job, we don't have that problem. And because it's all in a container, we know that code's not going anywhere. We can always pull that later if need be. So we're well set up to do it. Yes?
So, two kinds of questions. One is, what is fault tolerance of the computations? You're not using Hadoop or anything like it. And so there's that issue about, I understand that you're assuming that the storage system is fault tolerant. But the computations might fail, and then it's a question of, if the recovery is clean. And the other thing is resource management, I guess I'd say, is, okay, I need a bunch of containers, but each one needs, 30 gigabytes or something, in some use cases. Are you doing all that?
So there were two questions. One is basically fault tolerance. How much does the system do to prevent failures here? And the other question is resource management. How much smarts does the system give you in terms of this container gets this much CPU, this one gets this much memory? The answer is that we sort of don't do anywhere near as much as we want to with these things yet. We think that we're well set up to, mainly because we can know exactly like when a job is running and it fails. Well, so one thing that we do is when a job fails, that becomes what we call a cancel commit, which is exactly like a normal close commit, except it doesn't trigger anything downstream. And so what this does is it basically allows us to detect failures and make sure that they don't cascade, that the data is available for you to debug, and that the job can be rerun. That sort of happens no matter what because of version control and because you can always rebranch from there. And so I'd say we're sort of well set up and have the basics there. We don't have all of the like polish and nice user experience on that. In terms of resource management, we have done almost none of that so far. My understanding is that Kubernetes gives you incredibly good primitives, and I think really the first iteration of that for us is just going to be exposing the Kubernetes structure to people so that you can just say like this, you can set CPU code as within Kubernetes. But yeah, having that be smart, we would eventually basically like to make it so that you can have this like smooth sliding scale on a pipeline between saying, I want you to do this pipeline as quickly as possible, so maximize its resources and whatever, and I want you to do this pipeline as cheaply as possible, so like delay until spot instances are available, like run it sort of maybe one step at a time so we can do low memory and stuff like that. Yeah. Anyone else? Yes?
How do you store data commits? Do you only keep consecutive diffs?
How do we store data commits? We only keep consecutive diffs. I'm not quite sure what you mean by consecutive diffs.
Like following consecutive diffs. Do you only keep the diffs or do you keep also snapshots?
We only keep the diffs right now.
So if we have thousands of commits and we want to run the analytics on the latest commit, what happens?
So if you want to run it on the latest commit, basically it'll need to stream that data out. The thing that I think you're sort of getting at is that reconstructing this diff from 1,000 things could be really, really slow. And that's another optimization that we still need to make, is figuring out exactly how to do that in a big data system and how to cache that accurately, basically. Because, so what Git does, right, is they'll just sort of keep the like most recent version of the file, or like the version it had sort of lying around. Yeah, and for us that can be a little bit hard because that could be like a multi-petabyte file. So just keeping it lying around takes a lot more thought than just putting it on disk. But yeah, that's an optimization that we definitely want to make. Yes?
The example you showed, it was all with the shell commands. What if I wanted to run Spark jobs? How do you integrate with Spark?
So integrating with Spark, there's sort of, you can do that in terms of just running this like Spark within a container and using Pachyderm to get data out of it, or just using Pachyderm as a data layer and not using our scheduling layer on top of that. In terms of a true like good Spark integration, we're not quite there yet, because the problem is that we've sort of got our distribution, our like distributed computing model, and they've got theirs, and it's a little bit of a round peg in a square hole type of a situation, and like we'd have to sort of support their distributed model, or like have a way to have a Spark cluster running side by side with a Pachyderm cluster. We're not exactly sure what the best way to do it is yet.
Okay.
Yeah.
Okay, last question.
Last question.
Okay. So how do you partition the input data for parallelism? I guess what I mean is when I set parallelism on a pipeline as like 10, does that mean it's going to spin up 10 pods and partition my data 10 ways? Or is it partitioned by some like block size of the input file?
So the question was basically how do we partition data? The second thing that you said is pretty close to what we do. We basically break data up into blocks, and then when we spin up a job, you can request a parallelism. And what we will first do is we'll take that parallelism and see is every container in here going to have data to process. Right, and if it won't, then we'll keep knocking the parallelism down until every container does. And then, yeah, it's all just partitioned by the blocks, and each one of them is seeing a subset of the blocks. Cool.
Okay.
All right.
So,
Thanks so much, guys.
Sasha.
So you want to just, this thing's convenient. You probably. Yeah. Sorry.
If you guys want to sit, there's one of yours here too. You're totally welcome to stand as well. Also, if you need to use the restroom, it's to that side as you turn right.
Right, everyone, can you hear me well?
Yes.
Right. Just so I know the audience better, please raise your hand if you use Kubernetes or Mesos or any other orchestrator. Right. And please raise your hand if you use Hadoop or Spark or any other system I'm aware of. Okay. And please raise your hand if you use Docker. Okay. Thanks, everyone. So my name is Sasha, and today I'm going to tell you our story about porting analytics stack to Kubernetes. It's our experience. I hope it will be useful for you as you will start thinking about deploying these stacks, large complex stacks, to your orchestration system. So just a little bit about myself. I started as a founding engineer of Mailgun, and we sent a lot of emails to everyone, where we've been operating quite large clusters of a variety of stacks, including Cassandra, Kafka, MongoDB, which was a mistake, and others. So there I learned to optimize basically on the amount of times I wake up in the middle of the night. So that is my main metric when I choose my stack, basically. And if you're curious what's up with the BSD daemon, I'll tell you shortly. Okay, so today I'm going to focus on Kubernetes, and kind of everyone talks about containers, right? So we hear about them a lot. And I want to give everyone some a little bit of practical, kind of grumpy, ops-centric view of containers and orchestration and why should we all care about them, right? And one of the reasons I personally got excited about Kubernetes is I view it more just a containerization platform, right? I view it as a system that will soon become a de facto standard alongside some other systems like Mesos, for example. We'll see that soon, right? But it's no doubt that Kubernetes will become a sort of operating system standard, a POSIX standard for your data center. And it will actually simplify your life from operational perspective as an application developers. And today I want to tell you a little bit more about that. But I won't be talking much about containers, actually. Quite the opposite. I will tell you about other parts of Kubernetes in orchestration systems that are rarely mentioned today, or maybe they start getting some traction, and that's the reason we chose Kubernetes as our platform for the new company, Gravitational, that helps companies to go multi-cloud and release, distribute their software to go enterprise or private, to do private releases. So, when I was looking at Kubernetes and other orchestration system, the one thing that struck me about it was services. So what is that service and why are we interested in the service? So the way we can think about it, the services are smart, pluggable load balancers that we can rely on in our day-to-day workflows. We can imagine the service, and we are all familiar with it, if we, for example, deployed anything on AWS, or deployed F5 or HE proxy somewhere. That's exactly what service is. The good news is Kubernetes is not very opinionated about the implementation of the service. In fact, you will choose your service implementation, the load balancer implementation, based on the cloud provider. So if you deploy AWS, this will be Elastic Load Balancer, right, a private public one. If you want to go on premises, this will be HE proxy or IP tables or any other, maybe you can go as far as deploy real F5 and plug it in. I know that there are companies that are building plugins for that. So that gives us, application developers and operations system administrators and DevOps, all of us, the invariant that we can rely on. It's a very powerful concept if you think about it. There is a load balancer that never goes away, that we can always discover in the cluster, that smart load balances the traffic for us. And I will go to the smart part real soon. Another interesting part that is rarely mentioned is the way Kubernetes manages volumes and data storage, right? So we always always get to the point where we need to take a snapshot, right? Where we need to go and back up something, where we need to start thinking about high availability and disaster recovery and multi-data center, operations. At some point, we'll all get there. So again, that's the interesting part. Kubernetes doesn't tell you what type of volumes to use. Rather, it gives us powerful abstraction as a volume management, right? So we can say, okay, I need this volume to exist on the particular data center. I want to take a snapshot of this volume, and when my container moves around, the volume should jump with this particular container. Right? This is very helpful abstraction that simplifies our life a lot. Suddenly we don't need to think, oh, am I using Ceph, or am I using Google Cloud Compute Storage, or no, we don't need to think about that much. We only need to make this choice maybe once we decide our cloud provider or switch it. But then, application developers, we can just use these volumes as long as they work well and don't crash. The other interesting concept of Kubernetes and that particular standard is networking. Imagine you have two Nginx machines, right, and they Nginx services, or any other services that bind to the same port, or at least in all interfaces, as we sometimes do, right, and deploy our software. So what's up with the port collision? Now, if the scheduler schedules, two Nginxes on the same box, one of them crashes. Well, again, Kubernetes, when you deploy on a large scale, Google team realized, and this is one of the big realizations that they had, that you actually have to provide a special overlay network, reliable network between containers. So every container can get its own IP address. It's very powerful because suddenly you don't need to think about port collisions or any other troubles. When it comes to the real deployments, it's actually a big, big problem usually, right? And we solve that. But then the usual question is, what type of overlay networking are we using? Do we use VXLAN, or we use, AWS VPC overlay networks using routing tables? Well, the good answer is we don't need to choose, and Kubernetes doesn't tell us what to do. Rather, we can choose the perfect provider, right, with a reliable network. So we deploy on AWS, we're pretty confident in VPC, we'll start using it. And another thing that I personally love as someone who operates actually these clusters is events. If something happens to my cluster, I scale it up, or scale it down, or something crashes, or my configuration is wrong and I mess things up, I can always go back and see everything that happened in my cluster. I can go and see what happened to my load balancer, to my container, to my set of containers, to my node, to my set of nodes, to my scheduler. It's a very, very powerful concept, and you get used to it real quick. Okay. Another interesting thing that is not mentioned usually when we talk about containers is configuration management. It's such a big thing, it's such a big problem, right? If you use Chef ever, you know what I'm talking about, right? How hard it is to manage configuration in the cluster. Same, Ansible, Salt, Puppet. Well, config maps in Kubernetes allow us to treat configuration as a version object. We can change configuration, we can store these configuration snapshots, we can tell that this configuration version goes to this container, we can roll back to the previous version, and we can discover these versions. We can mount them in the container as file system, as event variables, right, as command line arguments. So we can plug in with all our existing systems without reinventing the wheel, right? Again, a great concept. Okay, so let's now talk about how all this greatness works in real life, right, with the real analytics stack. So that was the most complex stack I've ever encountered in my life, to be honest. So this stack that we worked with consists of Cassandra, actually DataStack's enterprise version of it, which is slightly different and slightly more powerful as it uses distributed file system. Spark, I learned that not very long time ago, but I was fascinated what it can do with Kafka, right? So with Kafka as a streaming abstraction, right, you get a replicated data stream, right, with cursors where you can consume them, provide streaming, various aggregations, logic, and then Spark can do aggregations with that and to take a snapshot on Cassandra DataStack's kind of distributed file system. And there are way more scenarios that I even don't know, but then how all that stuff really works in such an environment, right? Well, obviously there are challenges, right? And operating Cassandra cluster, has anyone tried to autoscale Cassandra cluster in production? Right. Has anyone tried to autoscale Kafka? All right. What about Spark? All right. So the only common thing with this system, right, it's enormously hard to provide automation for them because they're all super P-native. If you want to add one node to Cassandra and you have 3-node Cassandra cluster, that's one thing. If you have 400-node Cassandra cluster, then you want to add 5 more nodes, that is completely different story, right? So you can crash if you autoscale and add in, let's say for example you add a Cassandra node to the cluster, rebalancing starts to happen, right? And if your autoscaling logic starts to shrink that, well, all interesting things can occur. So, and I don't advise to do that unless you know exactly what you're doing. All of the systems, every system has their own very opinionated way to manage data, right? Cassandra, for example, you don't want to use volumes with Cassandra because it was initially designed to work with just plain disks, right? It will take care of rebalancing, hinted handoffs, repairs, and all that stuff. So if you put a volume there, you add another layer that makes it unpredictable. You do the same with Kafka, right? If you want to add, additional Kafka node or several Kafka nodes, you have to take care of Kafka orchestration because Kafka can be partitioned in a very different way, right? And you need to know exactly what's going on with these partitions. So you cannot just create a replication controller of factor 5 and then code there happens, unless you don't really care and then you just tell your ops, teams, whatever. I don't know what to do. I don't know what I'm doing, right? So how do we solve that problem with Kubernetes? This is where this nice daemon, you recognize this FreeBSD daemon comes, but it's not really FreeBSD in this context. Kubernetes is an interesting system. It gives us fine-grained control over everything that happens in the cluster. And there are 2 particular primitives that I really, really like. One is jobs, and jobs, right, it was mentioned by Joe in the previous talk. So jobs is a very traditional sense of the job, right? What it does, it starts up, if it fails, Kubernetes reschedules it. You can reschedule it multiple times. If it crashes, Kubernetes can give up if you tell it to give up, or it can continue indefinitely, right? Very simple. Daemon set is a slightly different beast. Daemon set allows us to say, hey, I want several instances of this particular process to run on every node in just one instance of that. Sorry for repeating myself here. And then usually it's used for things like logging collectors, right, or analytics collectors, where you need to have exactly one instance running and starting before everything else starts on the node. But wait, this is actually very similar to what Cassandra wants, right? Because it doesn't actually want to have multiple Cassandra instances, competing for RAM or for disks right on the same node, right, which is VM or physical machine. And probably it's the same for Kafka, right? Kafka is a very opinionated system. Actually, if you read the Kafka operations manual, right, so the way it needs to be deployed, it needs to take full control over the disk. It needs to make sure that it takes, has enough RAM and so on. So the way Kubernetes daemon set allow us to have this fine-grained control over what particular processes run on which particular physical nodes by using labels. So we can think of this process as saying, okay, please Kubernetes give me one Cassandra node, right? Cassandra node started up. We now carefully examine, was this, if we're bootstrapping the cluster, we now think, hey, how do you feel? Are you all right? Everything is good? Cool. All right, daemon set, let's add another Cassandra node, right? And let's connect that Cassandra node to the previous one. And by the way, let's check if they discovered each other and the cluster status is okay and ring status is okay. So the ring Cassandra is basically distribution of the data chunks, right? And then we add a third node and we repeat this process. If we want to shrink that cluster, again, we can remove the label from a particular node and slowly drain off the data and make sure that everything has rebalanced, right? And everything goes smooth, right? Here we go to this probes, right? It's another Kubernetes primitive that is super, super helpful for us to give Kubernetes a hint about this particular application. Because the fact that this container is running may mean nothing to Cassandra. It started, it may receiving some data, it's not even operational at this point, right? Or, if it's a Kafka, it's just started and it doesn't really mean it works. So we have to take care and give Kubernetes really meaningful hints about the status of this application, not just container, maybe a set of containers, right, running in the pod. We do this by writing, well, in my example, this is really a simplified version of that, but we can make node-specific checks, right, where we reach out to this node and try to connect to it and do something meaningful with CQL, right? So this node is up and running. And then we can do cluster level checks where when we edit a new node, we go reach out to node tool and see what do the other nodes in the cluster work. So if the cluster is healthy, rebalancing is complete, everything is right. So this is achieved by writing Kubernetes-specific probes, health and readiness checks, right? This can be as simple as writing a shell script, or maybe as complex as writing a real Kafka application that tries to submit data right on one side and receive the data on another side. Right, and then we go to services again, right? So we talked about Spark load balancing. What does it really mean in practice, right? Well, if you're familiar with Spark, I'm not sure if there's such thing you can do, by the way, as I'm not very familiar with it, but in Spark there is a thing called Spark master, right? So this is a very important process in Spark that controls pretty much everything, right? If it's integrated with DataStax Enterprise, DataStax Enterprise controls the life cycle of Spark master, right? So it spins up Spark, it can move this Spark master if one node crashed and so on. So what we do here, we can write a specific integration with this load balancer and make sure that this particular load balancer points to our Spark master at any given moment of time. So when we write our applications that needs to talk to the Spark API, we can just reach out here and make sure that it's pretty good implementation that always points us to the Spark master. So our application suddenly becomes way more from the complex application that tries to do discovery to the simple application that just looks at the DNS entry, goes to the virtual IP address, and just hits it. And this applies not only to Spark master, but to Kafka, to Cassandra, and we all know that their drivers are smart enough to do initial connect and do discovery on their own, right? So they need to connect to at least one node, and they discover other nodes. Right, and then we go to this, again, our pragmatic view of Kubernetes and orchestration frameworks gives us the ability to turn on features that really don't make sense for us. For example, as I mentioned, with Cassandra, you don't really there's not much sense in using network-attached storage, right? Because if you care about latency, especially, right? Or if you don't really know, like some providers cannot even guarantee that these are two volumes on these different machines really go to different SAN, right, drivers. They can actually go to the same SAN, and if one node crashes, Cassandra thinks that, oh yeah, I've got the cockpit, but in reality, no. Like there's a physical appliance which just crashed, and you lost all your data, right? So that is tricky. Let's just turn it off for some databases. The same, by the way, applies to overlay networks. If overlay networking is a problem, right, and we all know that they all come at a price, especially if it's some sort of VXLAN or any more sophisticated, encapsulation of packets, we can turn it off. We don't need to use that. Especially if we're talking about Cassandra, right, or Spark, right, that don't actually spin up two versions of itself on the same node, and we don't get these collisions. So what is the future of that setup, as I see it? And we actually see it in previous presentation where, for example, if you know Spark, it implements lots of these concepts itself, right? It has concepts of job, it has a concept of introspection into the host, right? It has some sort of understanding of what jobs are running on this particular machine, right? It takes information about CPUs. So instead of that, I think more and more systems will start using Kubernetes as their base operating system abstraction, so as their base cluster abstraction, in fact, right? So instead of writing your own job implementation, they will start using real Kubernetes jobs, right? And we see some of that already in Spark. For example, there is a plugin for Mesos, and I'm sure we'll see more of that for Kubernetes to use very soon. And there are new systems that are doing analytics, and they basically making the same choice, right? So instead of writing your own job system, why don't you use Kubernetes right away, right? So instead of doing your own node introspection, you can just get all the feed about the node status, RAM, CPU, hard disk drives, everything up to the kernel panics, right? Per second metric from Kubernetes. So we will use that. Very short presentation today from me. Thank you. Any questions?
So right now Intel has this new trend is SDI for NFV, Network Function Virtualization, right? And there is a new library which developed and there is everything. Where does Kubernetes fit in that? And how do you apply the Kubernetes on the new appliances which are getting built, like with the NVM over Fabric plus NVM over PCIe?
Okay, so the question as far as I understand it, how does Kubernetes play with all these new networking capabilities that are coming out there? Is that right?
Well,
How does Kubernetes work with all these new networking capabilities?
network functions virtualization.
Okay, I'm not familiar with network function virtualization, but
Because that basically strips down the layer of Kubernetes in a way.
is it an overlay network of some sort? Or
It's under layer. It's a lower one.
it's a low, it's like Ethernet fabric network?
Yeah, so you basically are virtualizing the network functions, running it on a higher level of the hardware.
Okay, well, I don't know anything. But that's an interesting question. Probably I can deep honestly. I encourage you to do the same.
So in terms of like the high availability,
Yeah.
what type of sort of like fault tolerance models do you have? So like if a network partition occurs and you have a split brain or something, how does that?
Well, it's very application specific, right? So
Yeah.
if we're talking about etcd, so Kubernetes it consists of a variety of components itself, right? So etcd, for example, if you've got enough nodes, right, running, so if you can maintain the quorum, so if only part of etcd cluster is experiencing partition, while you maintain a quorum, you can proceed, right? If you experiencing partition that breaks down your quorum, you cannot proceed, obviously, right? You can only read stale data, right? So that is one consideration. So if we're talking about Kafka has a totally different model where it contains this consistent replica set, right? So it keeps track of what particular nodes in the quorum have enough consistency, right? And it does its own failover. Then we can do Cassandra on its own. It actually is eventually consistent unless you're using transactions. So all this is a beautiful soup of systems that you have to kind of carefully consider how do you deploy them, right?
So it's sort of like maybe a plugin model then, where like each system has its own specific set of rules that define whether it's healthy or not, and then how it's spun back up somewhere else.
Yeah, that's why we need to kind of for Cassandra, for let's say for Kafka, our metric would be if there is enough, can Kafka continue? So if there is enough leaders, and you will be watching this replica kind of leader set as they call it, I don't remember exactly the name. Right? For Zookeeper, you'll be watching the different metric. How many can system maintain quorum? For etcd, you'll be using cluster count, and then you will do some sort of intersection of all this, and that will be your real availability guarantee, right? And consistency guarantee, which will be a tiny subset in reality, right, of every particular system. And then your failure probability increases, right? Because you need to multiply the probability of failures really, right? As far and your real kind of resiliency goes down with the amount of components really fast.
You mentioned about the putting these Kubernetes in production in big systems, right? So how do you face the production implementation with a hybrid solution when you have actually when you are running Kubernetes, you say, okay, we don't care for the networking layer because Kubernetes manages the networking layer. What if you do care? What if you have a hybrid solution? What if you have your networking components running on-prem, your A10, your F5s, whatever your database running on-prem? You have to give Kubernetes full control of the /8 network to run containers everywhere, but you still have your own stuff running there.
Well, again, you can if you can rely on your implementation of overlay network, right? For example, if you trust VXLAN enough in your system, maybe it's powered by real hardware, right? Instead of new kernel-based features, right? So why don't you give Kubernetes power to basically get control of the control plane and let's spin up the subnets for every particular node that comes up. So that basically goes down to the amount of trust you have in your overlay network and your load balancer. If you trust your F5
well, that pretty much is the same as moving whatever you had running on-prem before Kubernetes into Kubernetes as well, right? The question is, can you have both aspects of the on-prem components running and add some sort of Kubernetes to manage all
yeah,
those?
you can make a gradual transition, right? So, for example, you can run your existing overlay network and give Kubernetes access to the control plane of some subset of this network, of the same network, right? So then your existing systems will use the old deployment strategy, and your new systems will use the new Kubernetes managed kind of deployment system through the plugin, right? So they'll be literally talking to the same control plane, right? And at the end of the day, you're using exactly the same network. So the good example is, like, not on-prem, but on AWS, you're using exactly the same VPC and updating the same routing tables, really, right? So it's as reliable as AWS gets, and it's as reliable as your overlay network gets. Because if Kubernetes goes down, right, if you just, let's say we just crash Kubernetes, right, nothing happens. You're just losing the ability to autoscale and redeploy the cluster. But Kubernetes itself, and Docker, by the way, like by default itself, right, doesn't need your container to be there. Like, doesn't need to watch the container. Docker actually does, right? If you crash daemon, lots of things will go wrong. But if you crash Kubernetes, control plane, master, and standby, nothing happens. Everything keeps running. Load balancer stay, everything is up, right? That's the part I really like about it. It doesn't need to control everything all the time. Right, hope it was helpful. Thanks everyone.
Thanks. I'm